we are very fortunate to have Professor Jose Carrillo, who I hope I said your name right, from the University of Oxford. He is a tutorial fellow in applied mathematics at the Queen's College, the University of Oxford. And he has been in his current position since 2020. And we were just talking about how he moved there during the pandemic, during the height of the pandemic, you should say. And so prior to that, he was he held positions in various places, including at the Imperial College London. And he has research interests in kinetic equations and nonlinear non-local diffusion equations, and his talk today is going to be a little bit about that. But he has made several contributions to various areas in PDE, and he has been widely recognized and honored for his work. So he's a member of the European Academy of Sciences, a fellow of the Society of Industrial and Applied Mathematics. He's also a fellow of the Institute of Mathematics and its Applications, a foreign member of the Royal Academy of Sciences of Spain. And he has received several awards, including the Richard von Mises Prize, the Wolfson Research Merit Award of the Royal Society of London. And he was also a plenary speaker in the recent IKIAM held in Tokyo in Japan. And he has also received the very prestigious ERC Advanced Research Grant in 2019. So this is a very short introduction, and we are very lucky and fortunate to have Professor Carrillo here. And I request Professor Carrillo to start his presentation. So let me okay, so now you should be able to share your screen. Let me stop sharing now.
Yes, can you hear me?
Yes.
Perfect. Now I don't have any echo and everything is okay, good. Thank you very much for your invitation here. It's my pleasure. Thank you very much for the introduction. And I'm very happy to connect with former also people that I met at Imperial, like Harsha, that is around here also, the next speaker. So today I want to give you an idea, an overview on aggregation-diffusion equations. So the first half or even more part of my talk would be devoted to that. And then if I have time, I will describe briefly some new results in particular cases, which is this part on fast diffusion and partial concentration. But I think it's better to spend more time in the general picture of this field and what are the interesting questions. So let me see. Okay, yes. So the outline of the talk is the following. First, I would like to discuss this in the general framework of minimizing free energies and how this question of minimizing free energies is related to a certain family of partial differential equations. Then I will explain how to make use of scalings to identify different regimes for describing the asymptotic behavior of certain families of these PDEs. And finally, if I have time, I will concentrate on the new results in the latest 3-4 years, where we have a look at a particular range of the parameters in which you can have partial concentration of the mass on a Dirac delta or concentration for solutions or minimizers of the PD. Okay, so let's start with the basics. What do I mean by interaction energies? So let's start with an interaction potential. So let's U, capital U here, I'm assuming is a function that you can think for simplicity that is a radial function and that is only possible singularity you want is at 0 and even regular outside of 0. So think about the Newtonian potential if you want. At 0, you can give a value you want. It doesn't really matter. Given that potential that I assume is symmetric, I consider you, I somehow think about you as the interaction potential between particles. So say that you have m particles. The m particles are denoted by xi, indexed by I from 1 to capital N. And let's say that the action of or the effect of one particle xj onto a particle xi is given by the gradient of this potential. So I'm thinking about this term, gradient uxi minus xj, as the force exerted by the particle xj onto the particle xi. Depending on what you are modeling, this could be a force, it could be simply an effect, it could be different things. But nevertheless, this is all encoded in the shape of the potential U. So this is the effect that the presence of the particle Sj has on the particle Xi. And now I multiply by certain strengths that you can think about them as the masses of those particles. And then I sum them up, avoiding the term Xi, because I want to avoid self-interaction. So you want this the sum of all the forces acting on the particle Xi. Okay, so you can you may be wondering why I have a first order PD here, or sorry, OD. Well, I mean, this is you could think of starting with Newton's equation with damping, in which you have assumed that the inertia term is negligible, and because you have the damping, you then get a first order dynamics in time. So xi dot is directly equal to the forces acting on the particle. Okay, so nevertheless, I want to talk about the PDE associated to this system of particles. There are procedures to get rigorously from evolution of a system of particles, the evolution of a probability density or the mass density of particles. But let me do it formally at this point. Let me just say that instead of having m particles, I have now a density of particles at time t, either mass density or the probability density of finding a particle at position x. So I mimic the same construction I did here. So I say that each infinitesimal part of the mass, rho y, is producing a force at location x, which is given by minus the gradient of ux minus y. By the way, I didn't mention about the minus sign. The minus sign is just a convention in such a way that if the potential is decreasing as a function of the radius, then at that distance, the force is repulsive. And if the u is increasing as a function of the radius, at that distance, the force is attractive. Okay? So then, anyhow, this is producing a force. The mass located at y produces a force at location x, which can be attractive or repulsive depending on the derivative in the radial direction of this function u, the potential. And now I sum all the forces, meaning I integrate. And this should define the velocity field associated to this density rho. So what are the continuum dynamics associated to this particle system if I send the number of particles to infinity and I do some kind of a scaling limit that is called the mean field limit? One can prove, under certain regularity assumptions on u, that what you get is this kind of equation. Okay, so what you get is a continuity equation, just a continuity equation for the density of particles rho, where the velocity field now is coupled to rho itself and is coupled through this formula, which means that the velocity field is given by the convolution of minus the gradient of interaction potential with the density rho. Okay? So now we get a nonlinear, non-local equation, which is which type we could say is kind of first order equation. It's a kind of drift equation. It's a kind of transport equation, but it's a funny equation because it's not a conservation law directly. It's not a drift. It's a non-local term, what you get here. Okay. So let's see that also this is connected to other questions and other equations. So what do I mean? Well, by the way, this equation is what we usually call the aggregation equation, because this name came from the case in which the potential is fully attractive, that normally leads to concentration of the densities into particles, but also it was more generically referred with this name, even if the U is repulsive attractive. Then what is the aggregation-diffusion equation? The aggregation-diffusion equation can be written also as a continuity equation. Now, where the velocity field is given by the non-local term that I just had in the previous slide, and a local term that models diffusion between particles. I will explain why this. Okay, so if you think in terms of fluids, this is like introducing a pressure by Darcy's law. Okay, so you are saying that the velocity field is the gradient minus the gradient of a nonlinear or a function of rho. But also you can think about particular cases. Let's think about the case in which P of rho is equals to rho. This is equals to rho. You have here minus gradient rho. You substitute it here. That term in particular will give you rho times gradient rho, modulo the sign, and rho gradient rho is gradient of rho square. So you will get modulo constants and signs. You get here the Laplacian of rho square. So you can see that you get a typical nonlinear diffusion, which is of porous medium type with exponent 2. So this diffusion equation can be, in fact, this nonlinear diffusion equation can be also related to the aggregation equation by taking the potential, separate the repulsive and attractive part, and making the repulsive part very concentrated at 0. So very, very strong repulsion concentrated at 0, but mathematically it means that you get as the potential a Dirac delta at 0. So that corresponds to nonlinear diffusion, in fact. Okay, so just summarizing, the family of equations I'm going to deal with in my talk are families of equations of this form, or particular cases of this equation, in which we are modeling repulsion by diffusion, by this term, by the blue term, while the attraction is encoded somehow in the non-local term. And now a natural question appears is, when do I have a balance between the repulsive force modeled by this term and the attractive force modeling by the non-local term? And that's what is about my talk mainly. So, okay. Yes, so the basic properties that this family of equations have is the following. Let's start with, well, I mean, I probably should start with the simplest one. At least formally, this is a continuity equation. So this conserves the mass of the system. So if I'm talking about a probability density, if I do it later on, I can assume without any problem that the integral rho is 1. And if I'm talking about non-negative functions here, I can think in terms of probability density. Always you could normalize if you want in that way. So the second conservation that you can see is that there is conservation of the center of mass. This comes from the fact that U is symmetric. So if you multiply by x formally and integrate the equation, you can think that the time derivative of the integral of x rho is 0, because the two terms disappears, the Laplacian term disappears because you can reconstruct a Laplacian with this term, and the other term disappears because of the symmetry of U. If U is symmetric, the gradient U is antisymmetric, and you use that. But there is a stronger information about this equation. In fact, there is a Lyapunov functional for this family of equations. The Lyapunov functional has a very interesting physical interpretation. You can identify the two terms of the entropy functional by the total potential energy, which is given by this formula, because this is U conv rho, which is the potential generated by the density rho, multiplied by rho, it gives you the total potential energy. And the 1/2 is just convenient to write the corresponding equation in terms of this free energy function, as you will see in a second. The second term, the blue term, is related again to the nonlinear diffusion term, the P of rho. And you will see how to choose, I will show you in a second how to choose phi in terms of P. So this is something that we realized long time ago. Is in fact included in a couple of papers that I did in collaboration with Robert McCann and Cedric Villani in 2003 and 2006. And we, in fact, gave an interpretation of this equation as the Wasserstein gradient flow of this free energy. I'm not going to enter into what it means really to be a gradient flow of this free energy in the sense of Wasserstein 2, but I just want to write the equation in a way that you can see that this is a Lyapunov function and why this Lyapunov function is important. So let me rewrite the equation. If the equation that I have before, this equation, can be written in the following way. I can identify the velocity field in a different way. The claim is that if I do the variations of this free energy function with respect to the density such that the mass is conserved, I get precisely the equation above. So if you do the calculus of variations for rho being an interval function, non-negative interval function with a given fixed mass, you can see that the variation is given by u composed with rho. That's why I put the 1/2. And plus phi prime of rho. And now if you choose phi prime in terms of P, verifying this property that P prime is phi second, then exactly what I have inside here is the expression that I need to identify the velocity field in the previous slide. So what I mean is that this velocity field is minus the gradient of the variation of f. So I can write the equation in that form. And not only that, is not only that I can write the equation on that form, is that now, if I take the time derivative of the function along a solution, formally speaking, then it's multiplying this by the variation, and then you can integrate by parts, and you can see easily that this should be minus the integral of rho modulus square of the gradient of the variation. Or in other words, minus the integral of the velocity field square multiplied by rho. So this is telling you that this function is a Lyapunov function, and it's a very good Lyapunov function. It's a straight Lyapunov function in a sense, because if the velocity field is 0, then there is no dissipation, and you should have arrived to a steady state. So how can you characterize then steady states, or more precisely, locally stable steady states for this evolution? The question now is clear. We would like to find at least local minimizers of this interaction energy, because as in any gradient flow in any dimension, they will be typically locally stable in the right distance, in the right metric for that gradient flow. Moreover, if we are able to identify global minimizers, better. So the question of balancing between attraction and repulsion now is much better defined. What we want is to find conditions on U, conditions on phi, such that I have global minimizers or non-trivial global minimizers or non-trivial local minimizers of this free energy. Let me just make a comment on the particular cases. Important cases of this function phi or of P would be power laws. So if I put a power law here, if you do the algebra, P is a power law. So what you get is porous medium type equations. If m is the power is larger than 1, if the power is less than 1, what you get is what is usually referred as the fast diffusion equation. If you put rho log rho, so the Boltzmann entropy, then if you do the algebra here and you reconstruct P, P of rho is just rho. Is a log of rho in this case. So if you put P of rho, log of rho, logarithm of rho, you get gradient of rho divided by rho. The rho cancels, and what you get is linear diffusion. So the linear diffusion corresponds to phi being the Boltzmann entropy, rho times the logarithm of rho. Okay, so this question about the balance between the two terms is a question that has appeared in many fields, which I'm listing here, and I'm not exhaustive here. And but let me say that the first two probably have been the most classical ones. The first one corresponds to very, very singular potentials, Leonard-Jones type of potentials, in which essentially the potential is even plus infinity for short distances and very singular. These has been discussed in terms of discrete setting, in terms in where the density is in fact a sum of Diracs. Because being so singular the potential, the interaction energy doesn't make sense because U is not even locally interval, and you cannot make sense of that interval. But nevertheless, there were plenty of results in statistical mechanics about crystallization for these very singular potentials. Probably the other source of classical results is the case in which you use as potential, interaction potential, the Newtonian potential, either attractive or repulsive. And this corresponds to applications that have been done in semiconductors, in astrophysics, and the famous model in chemotaxis called the Keller-Siegel model. More recent applications are for more singular potentials than Newtonian, for instance, that leads to fractional diffusion, and other applications like eigenvalue distribution for random matrices. Okay, so, yep. So let's now discuss about scalings. I want to concentrate on a family of PDEs, a subfamily of PDEs that has some homogeneity. So what I'm going to assume now is that both the kernel U and the function, the nonlinear diffusion function P of rho, they are powers. Okay, so let's assume that the P of rho is a power, so rho to the m minus 1, and that U is a power, which is modulus of x to the k. I'm dividing by k, and k can be between minus dimension and dimension, with the understanding that if I take k equals 0, I assume that this by definition is the log. And I put a constant in front of the potential, kappa, chi. Chi is positive, just to have a way of identifying how attraction and repulsion strengths are relative to each other. Okay, so it's just I'm gonna, in fact, in what I will discuss here, I'm gonna take chi as the parameter, and I'm going to assume that the mass of rho is normalized. So I take mass of rho equals to 1. Okay, so just by looking at the homogeneity of the two functionals, in that case, both parts of the functional, the red and the blue part, the interaction potential and the nonlinear, the entropy part, they have a certain scaling, except for the log. But for the log, it's similar in some sense. But they have a scaling, and then you can extract the dependence on lambda, on a sun dilation argument that you use, and you can check that you have different regimes. So you can check that depending on how m and k are related to each other, one of the two effects can win. In which sense? Let me start with what we call the diffusion-dominated regime. The diffusion-dominated regime is when m is larger than dimension minus k divided by dimension. What happens in that regime? What happens is that if you look at the energy functional here, then when you do a dilation of a density, you take a profile of a density and you zoom in, so you are making your density rho closer and closer to a Dirac delta, then the interaction energy and the full energy is becoming smaller and larger and larger in that case. So meaning that when you zoom in, when you make more concentrated your profile, your energy increases. This is what you can check because of the relation between the homogeneities. And because of that, what it means is that since we are doing an evolution of gradient flow associated to the energy has to decrease in the gradient flow. So it means it's not favorable for the PDE to produce concentrations because the energy increases. So this, in fact, this intuition, in fact, can be made rigorous. We have been able to prove, in fact, that solutions exist globally and that they lead to company supported stationary states in particular cases. That, in fact, I'm just listing here a few references. There are many other references to be listed here. But generally speaking, this is the regime in which there is nothing wrong happening as t goes to infinity in terms of concentration. And in fact, you can show that asymptotically, they just converge to certain particular states. If you are in the opposite range, in the complementary range, when m is extremely less than this value, then the opposite happens. When you concentrate a profile, again, when you take a profile and then you concentrate it onto a point, then the interaction energy is stronger than the entropy, and the full energy goes to minus infinity. It's not bounded below. So what it means is that it's more favorable for the evolution of the gradient flow to produce concentrations. And in fact, that's the case. It has been proven in many particular cases in that regime that you have what is called blow up. The blow up means that if you start with the initial data in L1 L infinity, in finite time, it will not be in L infinity, it will be unbounded. But the situation is much more complicated than that. You can have both blow up and diffusive behavior at the same time, depending on the initial data. So it's not so clear that every solution will produce blow up or not. It's simply not true. Again, some references are there. Finally, what happens in between? What happens when m is exactly equal to d minus k over d? These, let me just say first that this is the case of the standard Keller-Segal model. The standard classical Keller-Segal model corresponds to m equals 1 linear diffusion in 2 dimensions, d equals 2, and k equals 0, meaning the Newtonian kernel in 2 dimensions, which is the log. So you substitute 1, 2, and 0, you can see that you get exactly this relation. So this includes the classical Keller-Segal. But what I'm going to say works in general in this regime. What happens in this regime is that you have a perfect balance between the two terms of the free energy. The two terms, they have the same homogeneity. So now it's up to the parameter chi, the constant that was in front of the non-local term, to determine the behavior that is going to happen in the system, because now it really depends on the constant in front of the homogeneities. So in fact, that's the interesting thing. You can show that there is a critical value, chi, c, that separates completely two behaviors. If chi is less than chi c, you have a diffusive type behavior, and if chi is larger than chi c, what you have is blow-up behavior, like in the aggregation-dominated regime. Okay, how can you identify this and study it mathematically? This is what I'm going to say is part of our work with Vincent Calves and Franka Hoffman that appeared some years ago. And let me just explain to you a little bit from where it comes. We are working here in the, as I said, in the fair competition regime. So we have exactly this relation between M and K. And here, as I said before in words, what we know in that case is that the free energy functional is homogeneous. This rho lambda means just a dilation of rho. So you just scale rho keeping the same mass with the factor lambda, such a way that you either contract it to a Dirac or you just diffuse it. And in this case, what you get is that it's homogeneous, or the exponent minus k. So this already tells you in the case in which k is between minus dimension and 0, when is singular, that all stationary solutions and global minimizers they exist, they have 0 energy. So let me just now make a comment on the Keller-Segal case, on the classical Keller-Segal case, this corresponds to the case in which k is equals 0, m equals to 1, and dimension is equals to 2. Specifically, there are some variations of this in other dimensions, but mainly in 2 dimensions. And there have been a whole study of this equation by many important researchers in analysis of PDEs. I'm just listing some of them, but I don't mean to be exhaustive here. And the conclusion of all these studies, at the end of the day, put it together, can be summarized in these 3 bullet points. As I said before, there is a critical parameter chi, in which you can prove that there are infinitely many stationary states. You can say that if chi is larger than chi c, you have finite time blow-up generically. And if chi is less than chi c, there are no stationary states. Solutions diffuse like the heat equation as t goes to infinity. So, and again, how can we identify this chi c? So let me give you a little hint on this. Don't try to read every information that is on my slide. Let me just focus on the inequality. This is very much related to the critical case of, optimizers, identification of optimizers of certain Hardy-Leibov-Sobolev inequalities. So the variation of the Hardy-Leibov-Sobolev inequality I want to study is this one, that you can obtain by simply apply the standard Hardy-Leibov-Sobolev, HLS, to the double convolution with a risk kernel when k is between minus dimension and 0. And then you can see that this is applying that inequality with p equals q equals to that number. You can get that this is less or equal than a constant, the LP norm square. And then the p, you can see that is between 1 and m under the condition I have on m related to k. And then you can interpolate it between L1 and Ln. And you can see the corresponding exponents to make this homogeneous. Okay, so that's how would you get the inequality. But the question is that that inequality on its own has optimizers, and that's where the surprise enters, has optimizers and an optimal constant, which is different from the standard HLS inequality. You can show that this constant here is smaller, strictly smaller than the constant of the HLS. And you can identify also the optimizers or characterize them in terms of elliptic equations, giving you the value also of chi c. In fact, one can prove that the chi c is very much related to the fact that the free energy function is bounded below or not by 0. So it's equivalent to have the HLS inequality to have that the free energy is larger or equal than 0. And that's how you identify the chi c, the chi that makes exactly these to be sharp, the positivity of the free energy. Okay, so with this, essentially, this I can tell you a little bit in words what's the status now on the study of this family of equations. And I have this kind of diagram in which, let me explain you things here. The red line corresponds to the line of homogeneity, the m equals 1 minus k over dimension. I was discussing mainly the case in which k was between minus d and 0. Between minus d and 0, I told you that this line corresponds to this HLS inequality that gives me the system of this critical parameter chi, making a dichotomy between blow-up and diffusive behavior. Over that line, when m is larger than the corresponding value, 1 minus k over dimension, is what is called, we call the diffusion dominated case. Here is the area in which you convert to steady states. If you are below, here is the area in which either you blow up or sometimes you may even converge to, diffuse to 0. So somehow these lines divides exactly and sharply these two behaviors. So this is part of works that I did with my former PhD student, Franca Hoffman, and collaborators, Eduardo Mainini and Bruno Bolzone. And what I want to emphasize now is that I would like to discuss what happens now if M, if the exponent becomes less than 1, is what I call the fast diffusion regime. Why that? Because I mean, it makes sense to look at that range in terms of the applications that it has also in math biology. You could think about Levy flights or particles that are distributions that have thick tails. And that some of them will correspond to a fast diffusion regime. So it has an interest, and also from the mathematical analysis viewpoint, it's interesting to see what happens when you change, because as I will explain you next, the free energy changes somehow its behavior radically. Okay, so in the last part of my talk, which I want to just explain you some things that we have learned on this regime of the fast diffusion case. Okay, so I already, the title tells you something. Diffusion wins, but in which sense and when? That's the question. Okay, let me first comment on, before getting this slide here, on the formula again of the free energy. If I go back to the free energy, oops, I probably don't have it. Yeah, okay. I don't have it explicitly written in these slides. Sorry. So better not to do it. Okay, I just hesitated. Let me go to the free energy formula. Here. Okay. So one can check that if M is larger than 1, in fact, the term here, the one corresponding to the diffusion, in fact, has to have a constant in front. So it's rho to the m, and it's not only rho to the m, but it's rho to the n divided by m minus 1. While here, you will get modulus of x minus y to the k divided by k. So when you go to the regime in which m is less than 1, the constant in front changes the sign. And that is somehow crucial, because now if I want to bound from below the free energy, that if you remember, that was the most important thing in the porous medium equation case, then I need to find other inequalities rather than the HLS inequality. If I wanted to estimate the free energy from below, this was a good idea because I was estimating the interaction energy, because F will be the rho to estimate the interaction energy in the case in which M is less than 1. I want to estimate it in terms of the Ln naught, because I want to estimate the free energy from below, as I said. So I want to estimate this term in terms of this term to say that this quantity is larger or equal than something, in particular larger or equal than 0. But if now the sign of this changes, I need the opposite inequality. I need to control this in terms of that. And because not only I want to make m less than 1, but I want to see what happens when k is positive now. Because you see the k, precisely this relation tells you that if m is less than 1, the k has to be positive to keep this relation. So if I want to look what happens in this regime, in this area, yeah, k positive, m less than 1, the two terms have changed sign. So in short, I need to find an inequality which is in the other direction. So I wouldn't say it's the wrong direction. It's just that it's a different inequality in a different regime of exponents. So this is what we referred as the reversed HLS inequality. So now the question is this inequality true? Can I estimate the integral of rho to the m in terms of this quantity, which is a kind of non-local moment of the density rho, because now k is positive, with the help of the L1 norm. So it's precisely the reversed inequality with respect to before, but now we are in the range in which m is less than 1 and k is positive. Is this inequality true? So that's what we discover. This inequality is true. In fact, there was a previous result that I will refer in the next slide, in a particular, for a particular relation of k and m, in which this was already known. And that was known for some conformal geometry problem. And so we tried to see, okay, how much can we push that inequality? In which range of k and m can we get this inequality to be true? And in the result that we got, we can show that this reverse inequality is true if and only if m is larger than this value, d over d plus k, which you could see that it has nothing to do with the homogeneous, the homogeneity curve, red curve that I had in the previous slide. It has nothing to do with the k equals 1 minus k over d. Well, by the way, here there are some typos. These capital N's should be just dimensions, okay? In fact, it's worse than that. Only in a subset of this range, we can show that the minimizer, the optimizer of this inequality, which in fact coincides also with the minimizer of the free energy, is an interval function. By the way, if somebody is worried about my notation here, I'm not claiming when m is less than 1 that this is a Banach space. This is just a notation. Lm over d just means that the integral of rho m is finite, even if m is less than 1. I'm not claiming that this is a Banach space. Okay, simply a notation. Okay, so let me explain you more carefully all of that. Now, as I said, this is a kind of extract of several of the results that we are able to do in this range. So if m is less than 1 and k is positive, this curve m equals d over d plus k that we obtain, that gives you that the inequality is true if and only if it's extremely larger, is this curve here. Okay, in black. Below that, in fact, what we proved is that the free energy is simply not bounded below, including the line. So the homogeneity line, even if it's true that here is homogeneous, it doesn't play any role because the free energy already, the infimum is minus infinity. Yeah, and this line is exactly tangent this curve at m equals 1, k equals 0. So we discovered that this homogeneity line now does not play any role, at least that we know for the time being, because the free energy here, the infimum is minus infinity. There are no minimizers on L1 such that the integral rho m is finite. Now, what happens in the upper part? In the upper part, we have the inequality, so the free energy is bounded below, and we know that the minimizer of the free energy is in L1 if is in the dark gray region. So if it's above this line here or above the blue line here. Okay. This red line, m equals 2d over 2d plus k, that is the family of reverse stage-less inequalities that was proven already before by these authors. Okay. And over these two in the dark gray region, above the blue or the red line, we can show that the minimizer is an L1 function. How we prove the existence of minimizers? We realized that we couldn't do it in general in L1LM, so what we did to prove optimizers or minimizers of the free energy, which is equivalent, is to extend the space. We extended the space to L1 plus possibly a Dirac delta at 0. And we were looking only for radial minimizers because it's easy to see that minimizers, if they exist of this free energy, they must be radially symmetric decreasing. So we added a Dirac at 0, and by adding a Dirac at 0, we were able to show that the optimizer of this inequality can be achieved in that set. You would be wondering what it means that it has a Dirac at 0 for this to be well defined. Here, of course, you can take a Dirac at 0 because this is simply a moment. The problem is here. Of course, when I have a Dirac at 0, what I mean by this is just the integral rho to the m, where rho is the absolutely continuous part of that measure. So you don't consider the Dirac at 0 for this nonlinear term. So the way in which we prove then this is by minimizing on that set, and you can show that the minimizer above the line m equals d over d plus k may have a Dirac at 0. What we just said is that we couldn't say when the Dirac at 0 is present or not, except in the dark gray region, okay? So in all this white region between m equals d over d plus k and the red line and the blue line, all over there, we didn't know if this Dirac is present or not in the minimization problem. And this was in this paper with Matthias Delgadino, Jan Dolbeau, Rupert Frank, and Franka Hoffman. So the interesting question now that remains is, does this concentration really happen? Okay, so let me explain you a bit on this. But before that, how many minutes do I have left just to adapt?
So if you can conclude in 10 minutes.
Okay, very good. So this is a recap of what I just said. So now written in terms of the free energy. The free energy associated to that problem, we can extend it by gamma convergence limits to free energy defined on the probability measures. Essentially, what it means this is that the free energy will have in the integral of rho m, when rho is a probability measure, we just take the absolutely continuous part of the measure. And in the moment, we take the full measure. And one can see that this is the extension. And we can show that there is bounded below if and only if is m is larger than d over d plus k. And there exists a global minimizer, but is of the form an L1 such that the integral rho to the m is finite, plus possibly a Dirac delta at 0 with certain mass between 0 and 1. And this is essentially what I said before. The mass is 0 in certain cases, but we don't know when there is a presence of possibly a part of the mass when the m star is extremely positive. So that was the question, can concentration really happen or not? So I wouldn't be discussing this if I don't have a positive answer, but my positive answer is still not complete. Let me just explain to you a little bit how we attack that problem. It's a minimization problem. So then how we thought about this is, okay, let's go for the Euler-Lagrange conditions. And let's see in the Euler-Lagrange conditions if we can identify somehow that the absolutely continuous part of the minimizer has some issues in terms of being interval, but that the mass doesn't achieve the maximum. So, which has to be 1, has to be a probability density. So if I prove that the absolutely continuous part of the minimizer has extremely mass extremely less than 1, I have to have the rest in the Dirac delta. So that was the idea, and then we look at the Euler-Lagrange equation for the absolutely continuous part for this variational problem, and I can, it has this form where rho star is that absolutely continuous part. We can identify the constant here. The constant here can be written in terms of the value at 0 to the power n minus 1. So this could be 0 if rho star at 0 is plus infinity. Rho star is decreasing, it's really decreasing, but it may have value plus infinity at 0. And that's L, and in fact, L is the Lagrange multiplier that comes from the constraint that we have on the mass. The mass has to be such that the integral of the absolutely continuous part plus the mass that comes from the Dirac is 1. And then what we did is to compute particular cases. The particular case that we compute was k equals 4. Why k equals 4? Because k equals 4 here can be expanded. We can just say, okay, k equals 4, we can expand it in terms of polynomials of degree strictly less. I mean, degrees 0, 2, and 4. Why that? Because when you span the fourth power here in the convolution, you will get the fourth order term, the second order term, and the zero order term only because the rho star is radially decreasing and radially symmetric. So then the third order term and the first order term disappear. So if you do that, you expand this, then the Euler-Lagrange equation is equivalent to say, in this particular case of k equals 4, that rho star to the minus 1 has to be a polynomial of degree 4, a very particular polynomial, as you see, because the coefficient written in this way has to be 1 for this power, for the fourth power, some coefficient for the second power, and L, the constant, is the same as here. It's given by the value at 0. And what is B? B has to be related to itself. B has to be related to the second moment of rho star. So there is a nonlinear relation here between this constraint here, and the fact that rho star to the power n minus 1, modulo the constants here, is a polynomial. So what we did is to apply, I'm going to just explain in words, and I will not will not show you any detail. What we did is to get rid of this constraint by saying that for every L, there is a unique B depending on L in such a way that this constraint is satisfied. So by a kind of implicit function theorem argument. So that's the first step. So use this constraint to reduce from 2 constants to 1 constant depending on L. So now in that way you have only one constant to be determined. And then what we check is how the mass of rho star E depends on L for each candidate to solve the Euler-Lagrange condition. With this, we have all the candidates to solve the Euler-Lagrange condition. The absolutely continuous part of our minimiser has to be one of them. So then we check how the mass of rho star depends on L, and we check if for every L larger or equal than 0, the integral rho star is larger than 1 or less than 1. If it touches, if it crosses 1, then that is the optimizer. And then there will be no concentration. But if all of them, they don't cross 1, so they are remaining below 1, then I can have the concentration at 0. That's the strategy of the proof, and that's how we identify the exact L that gives me the exact M, sorry, that gives me the possibility with respect to k equals 4 to have concentration or not. So the result of that is that we can identify a critical M, middle M now, such that if M is larger than that number, then the mass on the Dirac is 0. But if M is less than that number, up to the curve that we have from below, that it was d over d plus 4, then we have a little mass on the delta. So there is concentration. Moreover, we can say that the profile has to be of this form, and it has to be for L equals 0. By the way, I skip one thing, is that this function of the mass as a function of L is decreasing. So at the end of the day, I need just to look at the mass when L is equals to 0 to find this point MD4, and that's why in the case in which I have concentration, when I am below MD4, then the rho star has to be of that form, which has an interval strictly less than 1. Then the rest of the mass goes on the Dirac. For k equals 4, this concentration happens only when the dimension is large enough, larger than 6. And if the dimension is less than 5, you can just check that then you cannot find that. So let me just finalize my talk by saying just a comment that we check numerically with the Euler-Lagrange conditions for other even powers. Why even powers? Because you can play the same game, you can expand. The problem with the other even powers, 6, 8, 10, and so on and so forth, is that you have more constants to determine. For 6, you get 3 constants and you have 2 constraints, but only. So then, sorry, you have only 1 constraint. So then you have a 2-parameter family. And we didn't find the way to discuss the value of the mass analytically, but we can do it numerically. And then you can show that for k equals 6 numerically, you can see that concentration still will not happen for dimension less or equal than 5. But as soon as you get, well, in fact, how to read these lines is to see if the crossing point with the value 1 is to the left or to the right of this vertical black line. If the crossing point is to the right, then there is to the left, there is concentration. If it's to the right, there is no concentration. So for instance, for k equals 4, this is dimension 6 and 7. This crossing point is to the left. This means that there is concentration. While here for dimension 5, 3 and 2, there is no concentration. If you increase the k to k equals 6, you see that there is already concentration at dimension 4, but not at dimension 3. At k equals 8, if you do a zoom here, you see that there is no concentration at dimension 3. And if k equals 10, you see that there is the concentration in dimension 3. So numerically, at least, we expect concentration in any dimension if you would take k large enough. But we don't have an analytical proof of this fact. You can ask myself also, you can ask me, can I do numerics for different cases, different from even powers? You can do that. And you can show in that case also numerically that the concentration should happen if k is larger. And you have a kind of curve that is joining, you should have in this picture here. Let me go to this picture. I went too far here to this picture. What you can show is that you expect a curve over here in between that will make the difference between concentration and not. And this, we don't know how to characterize it variationally, and this is an open problem. So let me just conclude with just a list of things that I hope I have conveyed to you. I hope to have conveyed that aggregation-diffusion equations with homogeneous pressure and kernels are already quite rich and interesting from the variational viewpoint. That in the fair competition regime, we can have a dichotomy similar to Keller-Siegel, while if we are in the diffusion dominated, we don't have this kind of dichotomy, and we have stationary states. There is no fair competition regime for fast diffusion with a dichotomy. And for that, we can see that concentration can really happen, but we don't have a full characterization yet. And just to conclude, I want just to thank my collaborators in the different papers I discuss in these summary results. And thank you very much for your attention.
Thank you very much, Professor Carrillo, for that very nice talk, and in particular for making it accessible. I would like, so we have a few minutes for questions. So I would like to ask the audience to ask any questions. So please feel free to unmute yourself and ask your question. Alternatively, you can also type in the Q&A tab at the top.
So Jose, very nice talk. So
Thank you, Harsha.
So a quick question on this critical chi for the Keller-Segal model that you explained. So that
Yes.
depends on the dimension, right? The chi
Right.
c.
Yes.
So in 2-dimension, and also it depends on the initial mass.
Well, in the way I wrote it, the mass was 1. It depends on chi. So I mean, I was normalizing the mass, and then the criticality appears on chi. This is equivalent. If you chi, you put it to 1, you can put the criticality on the mass. So yes.
And have people characterized what this chi c for various dimensions are?
Okay, so chi c is known explicitly in 2 dimensions. Chi c is characterized as the optimal constant of this HLS inequality in any dimension, the one that I presented. But the question of computing explicitly the Sharp constant of the inequality is open. We don't know the Sharp constant explicitly. We can prove that there is a Sharp constant, and we can have bounds, but there is no explicit formula for the Sharp constant.
So, and in 2 dimension, it's 8 times pi or something.
Yeah, yes. It depends how you normalize things, but say 8 pi.
Okay. So now that you mentioned the Sharp constant, this chi c for the HLS inequality, people have done the stability analysis for this, where they do.
It depends on what you mean by stability. You mean the stability in terms of the evolution problem?
No, stability in the functional inequality.
In the functional inequality. Yes, very interesting. Functional inequality. So for the log HLS, this has been done quite recently. And in fact, it has been done by Eric Carlin and Figali some years ago. And there is a very recent paper of Eric Carlin, improving the result. For the variance of the HLS inequality I showed, I'm not aware of any stability result for the function inequality, but it's a natural question, and I'm sure people will look at it soon, because it will give you rates of decay towards stationary states of the corresponding problem with the critical chi. So that's the main motivation of Carlin and Figali and Eric Carlin for doing that for the log HLS, is precisely getting rates of decay for the Keller-Segal model.
Okay. And now coming to how you solve this Euler-Lagrange equations. So you are taking a particular approach to solve it for these even powers, right?
Yeah, the thing.
Why are they the only solutions?
Yes, because as you see, at the end of the day, it's quite explicit. Let me go back. So from okay, let me go back here. So the thing is, when, for instance, k equals 4, you can really see that it has to be a polynomial, and it's just that the nonlinearity now is only on a coefficient. B has to be related to the second moment of itself. So you see, the dimension of your nonlinearity has decreased a lot. It's not, you're not looking for, you can pose it as a fixed point on the second moment. You give myself, well, the formula that you get from here, rho star equals to this divided to the power 1 over n minus 1, modulo the constants. And then you say that B is given by the second moment of that quantity. And then you just need to do a fixed point on the second moment. So it's much easier because of that. And precisely that, in some sense, is what we do. The steps that I skip is to show that you can do the second moment in terms of L. So you can reduce to one constant, And then we just look at the mass of rho star in terms of L, and we prove that it's decreasing. So in that way, since the mass of the rho star L now is decreasing, then we can just check what happens with the mass by the minimal value of L that you can get is 0. So then the maximal value of the mass is corresponding to L equals 0, and we just can compute what's the mass is at 0, and then this will give me the condition that there is critical mass or not. There will be a concentration of mass or not. So that's how we proceed. In this case, it's just we are lucky enough that when you span in the convolution, you really have a super easy expression of the absolutely continuous part of the measure. So it's this polynomial. Does it answer your question?
Yes.
In other cases, if you write the Euler-Lagrange equation of other case, of course, then you get here a convolution on the right-hand side here, and then this is much more complicated to solve. And we don't know how to solve it. That's the difficulty.
And final question. So you have got these concentrations. So you are the name is faster diffusion, right? So somehow you should not, it should not lead to this.
Yes.
So is that
Harsha, very good comment. In fact, I forgot to say a joke that I usually say in my talk, which is that the fast diffusion, the name of fast diffusion is very bad choice. Why? Because power Laplace of rho to the m when m is less than 1 means fast diffusion if rho is small. But if rho is large, it means slow. It's the opposite. Yes. So the fast and slow is always relative to the size. So when they gave the name of fast diffusion 30 years ago, they were looking at diffusive behavior. So then they were looking at rho small. And that is true for rho small, rho to the n when m is less than 1 gives you a coefficient of conductivity of diffusion, which is proportional to rho to the n minus 1. And then it's small when rho, it's large when rho is small. But when rho is large, rho to the n minus 1 is small. Meaning that if you are very close to a Dirac, the Dirac is almost stationary for the fast diffusion. So that's why it allows concentration. So summarizing, fast diffusion is a bad name because it's fast for a small rho, not for large rho.
Thanks.
No problem.